Welcome to the third in this lecture series of 5 lectures, Adventures in Logic for Undergraduates. Now, I have found out that there are actually some graduate students here, and that's acceptable. I won't kick out any graduate students, even though this is Adventures for Undergraduates. We started off with the first lecture, logical connectives. Logical quantifiers was the last lecture. And this one is on Turing machines. And then we'll have 2 more lectures, same place, same time, 1 week spaced apart. And hope the weather is better, actually, in the last 2 lectures, for the last 2 lectures. And I want to remind you that the challenges I mentioned range from easy to major parts of courses, and I don't necessarily tell you which, or where in the interval, the open interval, most of them are. Okay, so we're going to present carefully and slowly Turing machines, and then we're going to make a move, a common move, that allows us to forget about all the details of what they are. Absolutely all the details. And that will be very, I think, very comforting for you. Okay, so a Turing machines were invented by Alan Turing, 1937, and there's several little different versions of it. We're going to follow a version a little later in 47 by Emil Post, which is just slightly different. And the remarkable thing is, although the model of computation it represents, Turing machines, is extremely primitive, and that, in fact, in some sense, arguably the most primitive, although that's an interesting topic in and of itself. Even though it's extremely primitive, there's a sense in which it's complete. There's a sense in which it's complete. Now, there are other senses in which it isn't, but there are some important senses in which it is a complete model of computation, at least from the theoretical point of view. Now, of course, if you go into a computer store and ask for a Turing machine, I recommend you don't do that. I think they'll kick you out or charge you, maybe they'll charge you some ridiculous amount of money to build one on order. But basically, you don't want to be doing that. So this is quite different than your PCs that you go buy in the store. But they all have their origin here. They all have their origin here with ideas from this. All right, so a TM, or Turing machine, consists of a tape, which is a theoretical object, okay, which is infinite in both directions, and which comes divided into unit squares indexed by the integers, okay? And a Turing machine also comes with a reading head, which always hovers over a square of tape and reads what is on that square of tape. Now, computation begins based on a program and an input. First, initialization takes place based on the input. And at any stage of computation, the Turing machine is going to be in a state. And each square of tape has a symbol written on it. And the reading head is on a square of tape. That's the architecture. Now, computer architecture has come a long way from this, but this is an architecture. And the idea of program and input, is still with us today. Okay, now, the states or state symbols are written Q0, Q1, Q2, ... Okay. And the symbols, or so-called tape symbols, are written S0, S0, S1, dot, dot, dot. So we have two kinds of symbols, state symbols and tape symbols. Now, initialization is based on the input only. It causes the Turing machine to go into state Q0, Q0, with the reading head put at square 0. And the squares of tape have symbols placed on them according to the input, which I'll describe the initialization, this initialization, based on the input in the next slide. Okay? Now, computation continues step by step according to the program. The reading head may change symbols it is reading. In other words, the reading head is able to write and may move left or right one square. The Turing machine's state may change, and computation halts if and when no program instruction applies. In other words, if the machine doesn't know what to do next, it stops. What else is it going to do? Okay, all right. And the output is read off from the symbols on the tape. The output is read off from the symbols on the tape. If computation never halts, then there's no input. There's no output. If computation never halts, in other words, continues forever, then there'll be no output. Okay, now there are slight variants in the way this is set up, but this is a very convenient setup. Now let's talk about how we start computation. So we start computation based on a program and an input. Now the inputs for a Turing machine vary from context to context, but one good choice is sequences of non-negative integers. Sequences of non-negative integers. This will include the case of strings from a finite alphabet if you just identify the alphabet enumerate the alphabet. 0, 1, 2, 3, so forth. So in some contexts, you see finite strings instead. We're going to take the inputs to be finite sequences of non-negative integers, and the outputs we're going to take as a single non-negative integer. Again, in some contexts, it's more convenient to take the outputs to be also strings and so forth. So let's just take this setup. All right, so let's say we have a sequence of non-negative integers, n1 through nk, and we use capital N for the non-negative integers all throughout the talk. Now, some motivation. S0 serves as what's called the blank. Okay, and S1 serves as kind of like a 1. And this is so primitive, by the way, that we think of non-negative integers as sequences of ones. We don't even use binary notation, okay? This is, of course, very bad for some other purposes, but for today, this is just fine. So here's how we initialize or start the computation. We initialize as follows. At square 0, we put n1 plus 1, because I don't want n1, when n1 is 0, I want something to happen anyways. I put n1 plus 1 S1s, in other words, 1, 1, 1, 1, 1, right? Followed by a blank, which is S0, followed by N2 plus 1 S1s, 1, 1, 1, 1, 1, followed by a blank, and so forth, all the way to N sub k plus 1 S1s, followed by all blanks for the rest of the tape. The whole rest of the tape is blank, meaning it has S0 on it, okay? S0 all the way, in other words, to the right, we have only S0. Now, to the left of 0, to the left of the square 0, we have all blanks, all S0s. So we have all S0s, and then we have this core of stuff that encodes or is based on or is a kind of loading of the input. All right? Okay, now I say there's something on the bottom here which is incorrect because the last line is incorrect. It needs to be changed. If k, no, I'm sorry. I speak too fast. That's right. If k equals 0 and there's no n, in other words, the sequence is the empty sequence, then I will have not done anything in this process, and so it'll be all S zeros, considered all S zeros. Yeah, I'll allow the empty sequence from n. All right. By the way, I know that you're thinking, oh, how am I going to remember these details? Sooner than you'll know, sooner than you will realize, I will tell you that you can forget about all the details. Okay, but I just want to be extremely specific about a model of a famous primitive model of computation. That's all. Okay, just to show you that there's some precision behind this whole subject. So bear with me with this. Okay, and just to make sure you don't completely forget, I got in small type, you know, everything I said about this setup there. All right, now, we still haven't talked about what programs are and instructions. Okay, so a program is made of instructions, and the instructions are quadruples. And there are three types of instructions. The first type is if the machine is in state QI and it's reading SJ, meaning the reading head is sitting over SJ, written on it, then move the reading head to the left and go into state QK. No writing involved. If instead, the second kind of instruction is, if in state QI reading SJ, move the reading head to the right and go into state QK. Okay? And the third kind of instruction is, if in state QI reading SJ, replace SJ by SM. This is writing. And then go into state QK. So if you write, you don't move, and if you move, you don't write. Okay? Now, obviously, the applicability of an instruction is based on the first two items. The last two items tell us what action to be taken. So in other words, I look to the first two parts, in other words, the first two items, QI and SJ, to figure out whether that instruction applies. Now, a program is a finite set of instructions where any two instructions with the same first two items are the same. And what does that tell us? That tells us that in a program, at most one instruction can apply at any given time. At most one instruction can apply. Because if you have the same first two items, you have the same quadruple. Okay. Now, that doesn't mean that always there will be some instruction in the program that does apply. And if there's no instruction that applies, I told you that you halt. We'll go over that, what happens when you halt. Right here. Okay, it's coming up soon. Halting occurs if and when no instruction applies. So you might be going on for, say, 3, 4, 5 million years, and then all of a sudden no instruction applies, and then you halt. So it may take a long time to halt. All right? Even at 1 cycle a nanosecond, you could go on for several million years and then halt later. Okay, this can happen. You can write small little programs that actually behave that way. All right. Now, we'll use capital P for programs, and we'll use the Greek letter alpha for finite sequences from n. And now we want to write val of P alpha. This is not necessarily standard notation. Val of P alpha, meaning the value of what happens when you use program P at input alpha. So if you use program P at input alpha, things go on, and if it halts, we get an output, and if it doesn't halt, we don't get an output. Okay? So val of P alpha might be undefined, or it might be defined. Now, I haven't told you how you get the outputs. I think I forgot to put this in here. My mistake. Okay, so what is the output going to be? The output is going to be the number of S1s on the tape. The number of S1s on the tape. That's a natural number, and that will be the output. There can only be finely many S1s on the tape, because if it halts, there can be only finely many S1s on the tape, because if it halts, only finely many squares could have been visited by the reading head. And since it starts off with only all but finely many squares with S0, if it only visits finely many squares, only finely many can be written into an S1. Okay. So I believe I forgot to tell you what the output is, and the output is, when after it halts, the number of S1s that remain on the tape, okay? And that will be fixed for the PDF file. All right, now, Turing computable functions. So it's convenient to let n star be the set of all finite sequences from n. And it's important to consider not only functions f from n star into n, but also partially defined functions f from n star into n, where f is defined only at some arguments from n star. So you're familiar with this idea of a partial function from a set to a set. It just means that it may be undefined at some places in the set. That's all. Whereas a function has to be defined everywhere. If you say partial function, it can be defined wherever you want it to be. It can be defined only at some places. All right, so we say that a program P computes partial f from n star into n if and only if each f of alpha is val of p alpha. In other words, f of alpha is the result of using the program P at the input alpha. And if f of alpha is undefined, then there has to be no halting. And conversely, if there's no halting, f of alpha has to be undefined. So that's what it means for a program to compute a partial function. This is what you'd expect it to be. Now, I call a partial function Turing computable if and only if there's a program that computes it. So it's Turing computable if and only if there's a program that computes it. And also, I can consider partial functions f from n to the k into n. Now, n to the k is just a small part of n star. Remember, n star is the sequences from n of any finite length, and n to the k is the sequences from n of length k. So obviously, partial f from n to the k into n are examples of partial f from n star into n. And we mainly want to study f, partial f from n to the k into n. That's why I mentioned it. We want to focus on partial f from n to the k into n. All right, we're now ready to get rid of and forget about all the details so far. There's a magic wand called Church's thesis after Alonzo Church. After Turing machines were invented, many richer models of computation were studied. Turing machines are inconveniently primitive. And it was shown that all of these models of computation, all of them, including Turing machines, lead to the same class of computable partial f from n to the k into n. The same class of functions. No matter how sensible you make these richer models of computation, you all wind up with the same thing. And there were a lot of papers involved which were very detailed and complicated in order to do this. So you have to simulate one model of computation in another. Is basically what happens. And as you know, the modern form of that is rather involved and complicated, you know, to go from one kind of code to another kind of code and so forth. So this whole project is still very much around. for practical study. But these are very theoretical basic models of computation. All right, now, on this basis, Alonzo Church formulated the thesis, and I think it was partly because he was editor of journals that had to handle these complicated papers. I think that was part of the motivation. Because of Church's thesis, we never have to go back to the definition of a Turing machine. The thesis says that any computable partial function is Turing computable, where I put computable in quotes. In other words, if it looks like a computation procedure described in mathematical English, even with some hand waving, it's okay. So that's what we're going to do. We're going to, do some obvious English discussion of how some computation runs, and just say, well, therefore, it can be simulated by a Turing machine because of Church's thesis. That's what we're going to be doing, which is a lot better than the alternative. The alternative is programming in some sub-machine language, which is, as you know, going to be pretty nasty stuff. All right, so we're going to use Church's thesis to obtain a number of elegant results, but before this, we will prove that, we won't actually prove it, I'll just state it. We will prove a theorem that strongly supports Church's thesis. It's my favorite support item. So the thesis is all computable partial F are Turing computable. Now there's a standard system of axioms and rules for all of mathematics called ZFC, and we'll discuss this in some detail in Lecture 5. Lecture 5. Suppose I have an intuitively computable partial F from n to the k into n. Now it seems clear that we should have a definition or description of F within ZFC, within mathematics, which is not only correct, but also has the following properties. If, in fact, f of n1 through nk is m, then ZFC ought to prove f of n1 through nk is m by simply running, you can, so to speak, run the computation and check in mathematics that everything was done right or something, right, like that. And also the other way around, if ZFC proves f of n1 through nk is m, then f of n1 through nk ought to be m. These are very basic things you would want. But there's a hardcore theorem now that if this holds for F, in other words, if there's a description meeting those two conditions, then F is Turing computable and vice versa. Okay? If F meets those conditions, in other words, there is a definition of F within ZFC which is not only correct but has those two properties, then F is Turing computable and vice versa. Furthermore, if this has nothing to do with ZFC, we can replace ZFC by any reasonable system with finitely many axioms, then F is Turing computable. All right, so this is a background. I hate to use the phrase that I proved Church's thesis because that's been a very hotly debated topic about what you mean by proving a thesis like this and so forth. But I will call this a justification. All right, so now we're ready to forget about the whole talk up to now, okay, and start again, armed with this Church's thesis. So in light of Church's thesis, we stop mentioning Turing, and all reasonable models of computation are the same as intuitive computability. All right, now the standard terminologies become the following. A recursive function f from n to the k into n. Same as Turing computable f from n to the k into n. Recursive function, and also partial recursive function is another standard word, f from n to the k into n. For Turing computable partial f from n to the k into n. Usually the partial comes in front of the recursive to indicate it's a partial function. Now, in some modern texts and papers, they use the phrases computable function and partial computable function instead of recursive function and partial recursive function. So don't get confused by that. All right. Now, when you're dealing with partial functions, you always have to be careful. Are things defined or not defined? You have to be a little bit careful. And so you use not only the equal sign, but you use the partial equal sign. Now, what does the partial equal sign mean? A partially equals B means either A and B are the same, or they're both undefined. Either they're the same and defined, of course, or they're both undefined. So that symbol is used now just to be careful with partial functions. Okay, so now let's do a simple little problem. Suppose f and g from n into n are recursive, then so is f composed with g. So here's how you prove this without, you know, in a nice way. We want to compute f circle g at n. We first compute g of n. So we start with n. We can first compute g of n, and then we stick that in as a argument to f and apply f to that. And since we already have algorithms for f and g, we're done. This is an algorithm. That's all. By Church's thesis, we don't have to mess with Turing machines or any other programming language. We don't, you know, we don't have to get worried about where we're going to store this, or are we going to have to erase the tape so we can set up the next computation? All that kind of stuff, you know. Operating systems, all that stuff, just gone. You just use English. Okay, that's how this subject is done now. English. All right, now suppose f goes from n to the r into n, and g1 through gr go from n to the k into n, and they're recursive. Then this generalized composition function, h, given by h of n1 through nr, is f of g1 through nk, dot, 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 g sub r of n1 through nk. That function h is recursive. And prove this. I'll leave you to prove this. So you start with input n1 through nr, and then you go do your thing, okay? And you should have no trouble saying this in English properly. Okay. All right, now, partial recursive functions. So let's consider f of g of x. In order for this to be defined, g of x is required to be defined. See, if g of x is undefined, then the whole expression is considered undefined. More generally, if I have a complicated expression like that, more complicated, it's required that all the parts be defined for the whole thing to be defined. This is a particular attitude towards partially defined mathematics, which is the right one. Although one has experimented with, the literature has experimented with other ideas, this is the right one. Okay, so now if f and g are partial recursive, then so is f composed with g. And you first compute g of n. If and when g of n gets computed, compute f of g of n. And you're fine if g of n never gets computed, because f of g of n was supposed to be undefined anyways. So you have to think about that. And then I leave you as a challenge to do the same thing when we have a generalized, what's so-called generalized composition. And you should think that through to make sure that the undefinedness works properly. So there is something to think about there, actually. All right, now we're going to talk about conditional branching. Okay? If, then, else. So conditional branching is written using if, then, else. Mathematicians usually call it definition by cases. Computer scientists call it conditional branching. So if we write something like if n is 5, then m, else r, that defines a function of three variables, n, m, and r. And it's m if n is 5 and it's r otherwise, right? Okay, standard programming construct. All right, now a little bit more complicated. If n is 5, then m, else if m is 7, then r, else t. In other words, you're allowed compound if, then, else. very commonly done. Now this is a function of 4 variables, n, m. This defines a function of 4 variables, n, m, r, and t. And it's m if n is 5, and it's r if m is 7 and n is not 5. And it's t otherwise. The rule with compound if then else is you go to the first place which is correct. You go to the first place which is correct. You don't execute the 3rd place unless, say, the 5th place, the 5th clause unless the first 4 clauses are false. And then at the end, there's this else thing where you just, if you ever get to there, you just put out t, right, in this case. All right, so we can do a conditional branching theorem that says that if I have a conditional branching, if all my ingredients are recursive, then the whole thing is recursive. And so we have a big compounded length R if then else. And I suggest you can think that through. Now this is not involving partial functions. I didn't want to confuse you with that. There's also, you have to be be careful. There's also a version of partial functions. But I'm just talking about recursive functions, which means everywhere to find. Okay. All right, now we're going to switch over to sets instead of functions. The characteristic function of a set, written chi of A, is defined by, is 1 if a number is in the set and 0 otherwise. This should be a vector. In other words, little n should be a vector. It should be x, actually, because A is a subset of k tuples. So I probably should have written x instead of n. All right? So a set is called recursive. A subset of n of the k is called recursive if and only if its characteristic function is recursive. Okay? And that's an attempt to reduce the set part of the subject to the function part of the subject. But intuitively, it's better to think of it this way by the following theorem. A is recursive if and only if there's an algorithm which, at every x in n to the k, eventually determines whether or not x is an A. So here we say it's recursive if there's an algorithm that such that given any input, any element of the space, at a finite number of steps, it will tell you whether or not, yes or no, is it in the set or not. All right, now there's a theorem that the union and intersection of finitely many recursive sets is recursive, and the complement of every recursive set relative to the space n to the k is recursive, and also every finite subset of n to the k is recursive. The challenge is to prove these theorems. And again, prove them using mathematical English. Next topic is recursively enumerable sets. Now these turn out to be much richer. There are more recursively enumerable sets than recursive sets. That's what we're gonna actually show you. I'm going to show you why. We say that the official definition is a set is recursively enumerable if and only if it's the domain of a partial recursive function. If and only if it's the domain of a partial recursive function. And that's how you reduce the set situation to the function situation, or the partial function situation. And now, of course, we would like something more intuitive. So a theorem is that a set A is RE if and only if there's an algorithm which, when presented with a point in the space, x, it halts if x is an A and runs forever if x is not an A. I want an algorithm which, when presented with x, it will eventually halt if x is an A, and if x is not an A, it must go on forever. And you can prove in English that this is the same as the official definition of RE, of recursively enumerable. Now, if a set is recursive, then it's RE. Nice English proof of that you can come up with. Also, the union and intersection of any finite number of RE sets is RE. Also, very beautiful English proof. using Church's thesis, right? All right, now, notice I didn't say anything about complements with RE. But I did with recursive, going back, see? The complement of every recursive subset of n to the k is recursive in that last theorem, right? Notice I didn't say that. Okay. Which should make you suspicious that it may be not true. All right. There's a beautiful theorem here that tells you what recursive sets are in terms of RE sets. A set is recursive if and only if it and its complement are both RE. And we'll run through this English proof. If the set is recursive, then the complement is recursive because of what I said previously. Hence, both the set and the complement are RE because of what I said previously. Because I said previously, every recursive set is RE. Okay, so one direction is already present with what I said. Now let's go the other way. Assume that both A and A complement are RE. I now want to describe a procedure which, given any x in the space, will tell me eventually whether or not it's in A or not. Okay, so what we do is we look for x in A. We also look for x in the complement of A. Remember, they're both RE, so we can set algorithms up to look for them. Now, we don't want to spend all our time on one side or the other because we may pick the wrong horse in this race and go on forever and therefore never give an answer. We don't want to, so we want to sequentially timeshare. We can't actually timeshare in the sense of concurrency. So, as you know, there's sequential time sharing, where you work a little bit on one thing, leave your work in place, go on the other side and work for a while, and leave that in place, and then go back to the other one and continue, and so forth, alternate back and forth like that. That's what you have to do here. And eventually you will find out that X is in A, or find out that X is in the complement of A. Because it is in one or the other, and the algorithms work. We're assuming the algorithms work. And then, of course, you now have the answer, whether it's an A or not. So you should think about that, and you should be more explicit about the time sharing used. Well, I was when I talked about leaving your work, coming back to it, and so forth. That's what I meant. So that your challenge is to actually remember what I said. Okay? All right, next. The range of every recursive function is RE. And why is that? Well, given any n in capital N, I can apply f successively to all elements of n to the k and wait till I get the value n. If I do get the value n, then I know it's in the range, and if I never, I know then it's not in the range, and that's exactly what I want. That's what RE-ness means, right? But there's a problem here. What do I mean by apply f successively to all of n to the k? I have to have some listing of n to the k. I have to have a listing of all the k tuples that's appropriate for Church's thesis, right? Appropriate for computation theory. And I leave that to you to be able to do that. You can't just use any old listing. You have to use a so-called reasonable listing. Now, there's another theorem. The range of every partial recursive function is RE. This is harder because in the first one, I know that I won't get stuck on the computing the value of any f, of f at any argument, because f is already everywhere defined, right? So I won't get stuck. But if I try that when f is partial recursive, I may get stuck. I might get stuck right in the beginning. F of 0 might not be defined. So there's a problem. So it turns out you have to use a lot more time sharing than before. You have to use a serious dovetailed time sharing thing. Okay, and I'll let you to think about that. Also, every non-empty RE set is the range of some recursive function. That one you also have to do something clever that we haven't talked about, and that is you have to count the number of steps of computation and use the number of steps of computation, quote unquote, because remember this is all in English, in the procedure. So basically, the intuitive English version of all this has time sharing and counters have to be used in order to really get the subject going. Now, of course, you can do this all formally and in computer languages and so forth. Okay, now, there's a theorem called the partial recursive enumeration of partial recursive functions. This is a listing of all of the partial recursive functions, listing of all of them, such that the combined binary function, f of nm, which is f sub n at m, the nth function at m, is in fact also partial recursive. So it's a listing of partial recursive functions for which this binary function is partial recursive. And there's a reasonable enumeration without repetition, in fact, of the Turing machine programs, and it's customary to write them as phi 0, phi 1, and so forth. And then it's easy to see that where phi sub n is the partial recursive function computed by the nth program, by the nth Turing machine program. And it's easy to see that phi of nm, this function phi sub n at m, is also partial recursive. Because you say, load the nth Turing machine at argument m and proceed. Clearly that's an algorithm, intuitively, by Church's thesis. All right, so we do have this. And now we want to do something, also we can do this for the RE sets. There's a thing called the RE enumeration of the RE sets. And this is a listing of the RE sets A0, A1, and so forth, such that the set of all pairs nm, such that m is in an, is an RE subset of n squared. And the challenge is you can get this by taking domains. So an example is the domain of phi 0, domain of phi 1, dot, dot, dot. That's an RE enumeration of the RE subsets of n. I think I will go on a little bit longer, but if you have to go, and then there will be a PDF file and eventually a movie on YouTube. Okay, so if you have to go, but I'm going to have to go on a little bit longer. So it's very common to write W sub e for the domain of phi e. W sub e for the domain of phi e. And we have an RE enumeration W0, W1 of the RE subsets of n. Now here's an example of an RE set that is not recursive. Fundamental theorem from the early days of the subject. Look at the set of all E such that E is in WE. Weird looking thing, right? The set of all E such that E is in WE. Challenge, show that this set is also RE. Now I meant to put its complement with a new paragraph. I didn't mean it to be part of the challenge. Its complement is the set of all E such that E is not in WE. And the second challenge is to show that this set is not among the W0, W1, is not among the W0, W1, and so forth. Pretend that it is one of the WEs and get a contradiction. It's very similar to Russell's paradox and Cantor's diagonal argument. You know, all these things are basically the same. Okay? So this is not RE. So that means the set of all E such that E is in WE is an RE set whose complement is not RE. Now, since the complement of a recursive set is recursive, clearly the set of all E such that E is a WE is an RE set that's not recursive. Okay, I'll let you ponder that on the PDF file. Now, I think that I will skip this, let you go look at this, and I want to end with a small discussion of Hilbert's 10th problem. Hilbert had this fancy problem list of 23 problems in 1900, which is very famous, and to this day, many things are open, and it has had a tremendous influence on the history of mathematics. So there's this problem number 10, which in modern terms calls for an algorithm that determines whether a given polynomial with integer coefficients has a 0 at some integer arguments. Given a polynomial with integer coefficients and integer variables, if you like, does it have a 0 with integer in the integers? Does it have a 0? Meaning a place where it's 0. And we can rigorously formulate this problem because we can associate to every polynomial with integer coefficients, to every integral polynomial, we can associate in a very simple way a finite sequence of non-negative integers. Okay, you can use minus signs to make sure that it's non-negative. This can be done. And now we just have to ask the following question. Is the set H10, get it, Hilbert's 10th problem, is the set H10, the set of all integral polynomials with an integral 0, is the set H10 recursive? That's another way of saying Hilbert's 10th problem. Well, the first thing is H10 is recursively enumerable, and I leave that to you to prove that. That H10 is recursively enumerable. What you want to do is go search for zeros. However, it's RE and not recursive. I skipped a few slides on complete RE sets. Complete RE sets are RE sets that are very, very bad. They pack a lot of information in them, and they're not recursive. So Hilbert's H10 is one of these really worst RE sets. All right. The corollary, there's no algorithm for determining whether an integral polynomial has an integral 0. And there's another very important theorem, which is even stronger. Every RE set, every RE subset of n is the set of values in n of some integral polynomial. Every RE subset of n is the set of values in n of some integral polynomial. And the reverse is also true by essentially the previous exercise. The RE subsets of n are exactly the sets of values in n of integral polynomials. Now this is actually, 1970 this was finally proved after a long series of work by 4 different authors. And we don't think we have the right proof of this because the proof we have raises more questions than it answers. So, and usually, you know, when you have the right proof, it does raise questions which are then quickly or often fairly quickly answered, and there's more progress. So there's been a very little major progress since the 1970s in some fundamental sense concerning this. So my challenge to you is find a new proof of the corollary. Now I told you, I mean, this is, I told you some challenges are harder than others. Now, here's another challenge. Is there an algorithm for determining whether an integral polynomial has a rational 0, i.e., can I find rational arguments that evaluates to 0? Can I find rational values of the variables for which it's 0? Probably not, but this has been a wide open problem ever since Hilbert's 10th problem in 1900. Hilbert's 10th problem for the rationals has been wide open, and maybe there is some progress on this, but I think that we're still at some distance away from being able to answer this problem. But I think conventional wisdom is probably not. There's no algorithm for this either, but this is an open problem. So that's even more, that's a really tough challenge for you. All right, so that's what I have to say today, and we will continue. This will be, the PDF file will be on my website as usual, and we'll continue, meet again a week from now on Gödel, Kurt Gödel.